In this video, I'm going to continue discussing the ontology problem, and in particular how it relates to the measurement and locality problems. So we'll start first talking about the measurement problem. So recall that the measurement problem, that we have the particle wave function in the nth eigenstate. So in this one, we'll be talking about the energy eigenstate. So we're in the nth eigenstate, so the pointer will be pointing at the E sub n energy. So we obtained this as our wave function in a previous video right here. And so remember, we're talking about sort of a generic measuring device that looks like this, where we have the particle here, we have a probe that interacts with the particle, and then the pointer that will point to some value that we are trying to measure. In this case, we'll be thinking about energy here. And so, which this means that the particle remains in the nth eigenstate while the pointer moves a distance of this and is now centered at the y sub naught plus this. So if we are saying on our pointer that, pointing like right here is the y sub naught, then it'll be pointing at some, y sub n there when it's actually measuring the energy. But if the particle was not in a definite energy state, so it's in a superposition of energy states, we then have that the wave function at time t equals 0 is this right here, where we have this. This is the wave function, the psi. This is our pointer right here. So at time t equals 0, the wave function is in this superposition. Then at time t equals capital T here, our pointer is now in this superposition as well. So it's sort of pointing at all of the states at once. So the pointer, or in the superposition of states, the pointer is pointing at y1, y2, and y3 all at once, if we're saying that we have a 3 energy superposition here. So what we assumed in the earlier video was that we could discuss the particle and the pointer as two individual substates of the overall psi of x, y, and t, where x is the particle position and y is the pointer position. That we could then peel these apart and examine them individually, but this in general is not possible. So there are overall states, such as entangled states, that are not separable like this. So if we take the quantum mechanical description literally, then the particle pointer system is just described by psi. It's not described by sort of two separate things. It's described only by the overall wave function psi. By this we mean that regions of the abstract space have high intensity, so whatever that might mean, depending on sort of what we're measuring. And so we see these two abstract spaces here, where the left is the configuration space for when we are at a definite energy here with our n equals 2. And so the x-axis, the horizontal axis here, is the position of the particle, and the y is the energy of the particle. And then, so the right is when we are in the superposition of the three states here. And so we can be in these, well, in all three of them, the particle would be in the sort of same position, but then it would be in this this superposition of these three energies, where, of course, the position itself is a superposition, which is why it's sort of smeared out over the x-axis there. So even in the left image, which is supposedly an unambiguous state, it's unambiguously in the y sub 2 energy state here. It doesn't really look like a particle in a box and a pointer pointing at some value, each of them moving in 1D space. And so, you might say, like, the particle, a single particle in an abstract configuration space doesn't look like a particle in three-dimensional space either, but what makes this different from particles in configuration space, which are also abstract, is that in that case we went from the concrete physical reality of the particles and then we abstracted them. So we have particles in our, three-dimensional space, or in the last video we were looking at sort of one-dimensional illustrations of it, but we went from the sort of real space and then we abstracted it. So then we sort of derived the abstract space from the physical space. In quantum mechanics, all we have is the abstract space, but we don't really know of a way to represent it physically. So we do not yet know what sort of real actual objects in 3D space the wave functions are supposed to be an abstract representation of. So Norson, whose book I'm following for this series, says, pointing out that quantum mechanics suffers from an ontology problem is thus largely a plea for help. Anyone who says that quantum mechanical wave functions should be taken seriously as corresponding in some sense to physical reality as opposed, for example, to our incomplete knowledge. So essentially, if anybody say that there is some ontological reality to what the wave function refers to or describes, instead of just saying that the wave function is just talking about our incomplete knowledge of the system. So if a person is saying that, then they should be asked to explain in concrete, mundane detail how that alleged correspondence works. So the correspondence between the wave function and the actual physical reality that it's supposedly describing or referring to. So they should tell us what sorts of things, particles or stuff, fields, quantum mechanics is about, and clarify in precise mathematical detail the relationship between those things. So, the particles or fields or whatever our wave function is actually about, and quantum mechanical wave functions. Until or unless this is done, I think we have to admit that the connection with the three-dimensional reality of direct experience remains puzzling, not only for the final state described in the superposition equation we looked at above, but also already for the state described in the definite state position above, where this on the left was our definite state here. And so essentially he's saying that, this sort of ontology problem doesn't just apply to the weird superposition and entangled states where we can, have these sort of multiple states at the same time here, but it also applies to even what look like unambiguous states as well. So we also have the issue that in quantum mechanical pictures of things, locality is difficult to define. So recall in the video on locality and causality that we had this image here, where this chi sub 1 here is some event, which we can think of as a measurement here, and chi sub 2 is another event or measurement at some location far away from this. And so we saw that that Bell's sort of conceptualization of locality was this, that the probability of this chi sub 1 given a complete specification of all events on this slice here, this sigma, this capital sigma slice here, needs to be equal to the probability of getting, of doing this chi sub 1, of getting, say, like a spin up state, given the entire specification of that capital sigma and getting this measurement at chi sub 2 right here. So those things would have to be equal, which is essentially saying that this right here should not be affecting this right here in any way if they do not cross over this complete specification of events right here. And so if we have an entangled spin singlet state here, so we have particle 1 in Z up, particle 2 in Z down, or particle up in Z down, and particle 2 in Z up. So if we say that we measure our chi 1, so our measurement at chi 1 is particle 1 being spin up in the Z direction, then chi sub 2 is particle 2 being measured in the spin up in the Z direction. So we're looking at what happens if we are going to say that we measure both of them as spin up. And so according to quantum mechanics, the spin up state being measured for chi sub 1 given this complete specification of events on this space-time slice is 50%. So it's 50% it'll be spin up, 50% it'll be spin down. But quantum mechanics also says that if we have this complete specification of events on the space-time slice and we have that the chi sub 2 that our second particle was also measured as spin up, then the probability that we get spin up at chi sub 1 is 0%. Where, like I said, this is the complete quantum mechanical description of particle 1 over this slice of space-time sigma. So this gray slice of our space-time right there. However, when particles 1 and 2 are entangled, there is no such thing as the wave function of particle 1. So we can't peel apart the two particle state psi into two one particle states. So there is only just the wave function here that is, this combination of these, but there's no way we can peel these apart and talk about just one of these. It has to be this sort of combination of them here. Also, the wave function for multi-particle systems is something like a field in abstract configuration space. So what is even meant by the part of the wave function that describes what is going on in sigma? So there's no part of sigma that describes the wave function because the wave function is not in normal 3D space. So this sigma here is a complete specification of all the events in our, I guess you could call it 4D space-time. So it's just all of the events in 4D space-time there. But if our quantum mechanics is on this abstract configuration space, then no part of this sigma here is describing what's going on with our quantum mechanical system there. So even if we instead use this, so we're saying that now it's the complete specification of events on sigma and the complete specification of the abstract space of our wave function here. So we use that for both of these, including the one where we get the spin up for chi2. So instead of using these. So in other words, we say that the events chi sub 1 and chi sub 2 also take the configuration space of psi into account. We still get that that this probability here is equal to 50%, and this one where chi sub 2 is measured as spin up is 0%. So even if we take the psi into account, we're still violating Bell's definition of locality that these two things have to be equal because 0% is not equal to 50%, and so they're not equal to each other. And indeed, not only is quantum mechanics non-local, but it is not even local, since there is no clear ontology of how quantum systems move and interact in normal 3D space. And so what's meant by that is it's not even just if we have our particles, really far apart here that there is, some quote unquote spooky action at a distance. If we have our particles, like right next to each other, there's no, when we have a sort of multi-particle system, we don't know how to describe these sort of interactions between them, even when they are sort of local to each other. And so it's not just that it's non-local, but it's not even local. And so there is still the ontology problem, even if we, just sort of ignore this issue of being non-local. But anyway, those were sort of the ways that the ontology problem sort of ties in with the measurement and locality problem. In the next video, I'm going to discuss essentially two ways that people have tried to sort of sort out this ontology problem in quantum mechanics. One of them that I touched on in the previous video is one that Schrodinger sort of proposed as a possible way of interpreting the wave function that would sort of try to solve this ontology problem. The other one is actually quantum field theory, which is sort of, taking quantum mechanics and building onto that, making it relativistic and things like that. But as we'll see in the next video, that actually doesn't sort of solve our problem either. But anyway, I hope you found this video interesting, and I will see you in the next one.